Good morning, everybody, and welcome to the Long Coffee Break, our 15-minute webinar series on Thursday mornings. My name is Jason Long, and I'm a sales engineer with Long Building Technologies out of our Denver office. Before we dive into today's topic, I just want to remind everyone that last week we started doing live giveaways, and today we're going to do another one. So please stay logged in through the end of the presentation to find out who this week's winner is. Today, I'm joined by Doug Yost. Doug is a strategic account manager with Munters, focused in the data center market. Long and Munters have been partners for over 20 years, and Doug and I have had the privilege of working together for the last 5. So with that, I'm going to turn it over to Doug to introduce us to an exciting new product that Munters has brought to the market in the last year. Take us away, Doug.
Thank you, Jason, for that introduction, and welcome to everybody. Munters is a 60-year-old company worldwide, 28 manufacturing plants, 5 here in the United States. Started out in desiccant dehumidification, which we still do. And over the last 12 years, we've had a very interesting history of innovation and energy efficient systems, HVAC products for the data center market. We started off with our Munters indirect evaporative cooling system called Oasis that has deployed worldwide and hundreds of megawatts throughout the world. And today I'd like to introduce our newest innovation for the data center market, which is called the Munters Sycool. It's a split DX system. And the reason that we've introduced this to the marketplace is that we're seeing some trends over the next 5 years that the data center market is evolving towards. And I've listed some of them here, but one of the biggest ones is the use of water. Water is an extremely efficient refrigerant for the data center market. However, there are becoming sensitive issues around that. So Munters recognized that we needed to introduce a dry, meaning non-water-based system, and this is what we've come up with, because this has great impacts on the overall infrastructure, the cost and total cost of ownership for data centers. It's very high efficiency, lower PUE, and reliability make it an excellent system. And this is an example of what it looks like, the Thermosiphon Split Sycool. It moves 400 kilowatts of heat from the data center white space to the outdoors, the ambient, through the evaporation of liquid refrigerant and the subsequent condensing of that same refrigerant in a passive nature. Passive meaning that being the key word. In other words, we are able to do this with no mechanical cooling up to the point where the outdoor air equals the process air temperature. So when ambient conditions preclude using 100% economization or 100% outdoor air to provide that cooling, Sycool seamlessly transitions to a full DX-based system using digital scroll compressors.
So Doug, you keep using the term thermosiphon. Heat pipe technology has been around for quite some time. Explain to us how this is a little bit different.
That's a great question, Jason, and it is a little bit different. However, what we've done is we've taken a heat pipe and we've just made a circle out of it. So let me step through that process and what it looks like. We'll start at the bottom. So we have an evaporator section in a craw in the data hall. It sees continuous process air from the servers on a 24/7 basis. That refrigerant takes the heat and evaporates, and as that phase change happens, that refrigerant rises up to the condenser sections on the roof. There we use scavenger air or outdoor air to provide the cooling to condense that refrigerant back to a liquid. And when that happens, gravity simply takes over and it flows back to the craw section. And now you have a continual refrigerant cycle loop that's passive. There's no moving parts, there's no oil to move around, and no compressors, like I said, until the process air equals the outdoor air temperature. Here's an example of how that actually functions. So what you'll note is you have the evaporator coil on the bottom, which is included inside the craw units in the data hall. It's cold until it receives that hot air from the hot aisle containment off the servers. As that refrigerant picks up that heat, it vaporizes, and rises towards the condenser sections on the roof or around the perimeter. Then we use the outdoor air to cool that refrigerant back to a liquid, and then simply through gravity, it flows back down to the bottom of the cross section where the entire process starts over again. And it's a continuous loop, again, with no mechanical cooling required, no pumping, and no oil in that 134A refrigerant. Here's an actual example of how this looks. So what we have are the different phases of operation. So in the top half of the screen is the outdoor section, the condenser section, and the bottom half represents the data hall. So in the data hall, we're supplying cold air. Generally, it's 75 degrees supply, 95 return. That heat is picked up in the evaporator section. As I've stated earlier, it rises up and goes into a passive condenser. That passive condenser just simply uses the fans from the condenser to draw outdoor air across that and providing the cooling for the data center. When the outdoor air is no longer able to meet the conditions to supply the 75 degrees into the data hall, here's the secret sauce. This is where we use a brazed plate heat exchanger, a refrigerant to refrigerant heat exchanger as a heat sink that's close coupled to a DX-based system. And then we bring on active condensers to provide the cooling for the 134A refrigerant in the thermosiphon. And that continually process from 67 degrees or 65, depending on ambient conditions, all the way up to 95 if we're supplying 95, and then the DX system becomes the 100%. There are 5 separate stages of that cooling provided by the DX system, and it's all seamlessly done through our control system. And here's what that refrigerant flow actually looks like. So we have on the left-hand side an example of the liquid flow. So this would be the 134A refrigerant with no oil, no traps, flowing from the condenser section back down to the craws, just through the process of gravity after it's condensed back into a liquid. And here is what it looks like on the evaporator side, where it's evaporating, picking up the heat from the data hall and flowing back up to the condenser just due to the phase change. It's not pumped, there's no oil in the 134A, and there's no traps.
Let's talk about installation and maintenance for a minute. How does this compare, Doug, to a traditional DX split system? And do we have the same piping restrictions and rules of thumb, or is this a little bit different?
That's a great question, Jason. One of the things that Munters recognized is that we had to make this modular, easy to install, and competitive from the mechanical contractor, general contractor perspective, so that they would be able to compete against other systems. So we have made the condenser and the craw as modular units. The only thing that, other than setting the units, the contractors are responsible for running 2 gas lines and 2 liquid lines. It's Victolic coupling or welded coupling. Since we're using 134A, which is a medium pressure gas, it's up to the contractor to do that. Insulation is very light. It can be run through pipe chases, and the separation, I think, which is the most important aspect here, is from a design standpoint. The condenser and the craw can be separated by up to 500 feet of a combination of both vertical and horizontal separation. The active DX system, which is in the condenser, is short-circuited, short-cycled, and does not need to be addressed because it's all built in from the factory. Here's a closer picture of the dimensions of the condensing unit. And at 400 kilowatts of peak capacity, we are generating a PUE of 1.43 at a maximum of 105 ambient. So those are the worst ash rate conditions, and we're still generating a 1.43 PUE. 11,000 pounds and about 9 feet tall, 28 feet long. This is what the craw section looks like. You'll notice in my background, there's an installation of what those craws would look like. These are two side-by-side 1x3s to make basically a 2x3 module. It's rejecting 400 kilowatts of heat from the factory or from the hall. There's a vertical shipping split, so they ship in two sections.
All right, so here's where this solution really blows me away when it comes to energy efficiency and the ability to reduce operating costs. What we're looking at here right now is an energy profile for a project in Denver, Colorado. A couple project assumptions here are that we have 75-degree supply air to our data hall with a 20-degree delta T across the servers, so our return air is coming back at 95 degrees. And this graph shows us what the operating window looks like for economization and when we need to use active DX cooling. The y-axis shows us total energy consumed in kilowatts, and the x-axis shows us ambient temperature outside. The different color bars represent our different sources of energy consumption. So the green are our compressors for the active DX circuit. The red are our scavenger fans, which draw ambient air across our condenser coils, and the blue represents supply fan energy. So there's a couple key things to really take away from this graph. The first is that the green bars don't start until 65 degrees ambient. So again, what that means is that whenever it is cooler than 65 degrees outside, we're able to meet the total load in our space without using any compressors. The second is this yellow line. That shows us the amount of operating hours we have throughout the year based on bin weather data for Denver. And this shows us that the majority of our operating hours will be in the middle of that graph, again, where we don't have to use compressors to meet our load. So this is a really big deal because we're able to achieve efficiency numbers that typically we've only seen with indirect or direct evaporative cooling solutions. And yet we're able to respond to that customer need and preference to move away from a dependence on water usage. This is one of the reasons why we're really, really excited about this solution. And the other thing I want to just note here is that at Long, we have the privilege of working with many different manufacturers. And one of the things that sets Munters apart is their robust engineering team and the ability to run an energy analysis like this on a project-specific basis. So if you have a project coming up and you'd like to see something like this, just reach out to your sales engineer and we'd be happy to help you.
Thank you, Jason. One of the interesting aspects about the Sycool is the ability for it to capture and maximize the use of outdoor air to keep those compressors off. That's our whole goal because it reduces the power utilization effectiveness and gets it so it's very, very efficient for the customer. Here's an example of how that capture rate for economization is represented against one of our competitors, as well as a perfect environment. The green represents using outdoor air 100% of the time. On the x-axis, you have the ambient temperature, and then the total run hours are on the y-axis. You'll note again, as Jason has stated, that our competitor, which is a pumped refrigerant variant, has to bring on compressors at 43 degrees. Munters, however, can keep running 100% outdoor air up to 63 degrees, again, at these conditions. So that economization capture rate is critical. In addition, Munters has the ability to deploy this system all across the United States, and we have run energy profiles for most major metropolitan areas as well as where data centers are located. In Northern Virginia, where over 50% of all data centers in North America are located. Again, we see the profile here showing that the PUE is 1.17, which is excellent. And finally, we need to be able to look ahead from a product evolution standpoint. Munters will introduce a smaller variety in the 200 to 250 kilowatt range, and commensurately, the fan array will become much smaller. So from a retrofit standpoint, that will work out very well. We also have a downflow crawl system that would work for underfloor air.
All right, thank you, Doug, and thank you to everyone for tuning in. We know you're really busy and we're extremely grateful for your time and you making the time to spend with us this morning. Next week, Justin Moutet from Long will be presenting with Scott St. Pierre from ISO Air. They'll be talking about portable space air purification solutions. So we hope you can join us for that.